So last session we started with geomorphology, that is the first segment of physical geography. We have discussed in last class the definition of geomorphology. It is the study of scientific study of landforms. Scientific study of landforms is known as geomorphology. What is a landform? Any feature that is made up of rocks and is a part of lithosphere, that is outer layer of the earth, and is of natural origin. This will be considered as landform. So landforms, they come in different, they exist in different sizes. So we have orders of the landform, that is first order or second order, third order. This is also known as macro, meso and micro landform. First, second, third, these are macro to micro because the size of the landform decreases. Or we can say second aspect about the landform is landforms are classified based on their origins. So some of the landforms, they have been formed by the initial cooling of the crust. Second, some landforms have been created by the forces that are originating from the interior of the earth. These forces are known as endogenetic force. Some landforms are created by the forces that are operating from above, that is having origin in outer part of the earth, that is atmosphere or hydrosphere. This will be known as exogenetic forces. Okay. Now, so that was the classification aspect of the landform. So landforms have complexity and diversity in the sense that the evolution of the landform and identity of any landform is highly complex, and they are diverse. Diverse in the sense there are spatial variation of the landform from one region to other. Spatial variation means if I take a mountain, no two mountains of the world are similar, no two plateaus are similar. Even though the landform exists in the same location, they differ from each other. Landforms are like fingerprints, wherein even though two individuals are twins, but the fingerprints are different. Similarly, even though the landforms are existing in the same location, same region, they are not same. The landforms are not similar. That is why landforms are considered to be complex in their nature and their evolution. Complexity and diversity. This is the basic characteristic of the landform. Now, this complexity and diversity of the landform is responsible for making the surface of earth uneven, non-uniformity on the surface of the earth, right? Now, suppose this is a landform, this is a mountain. Now, what is this? If you consider the height, the difference of elevation from the base level, I have given the definition of this. This will be known as a relief, right? Now, if there are multiple landforms in any region, different types of landform in any region, that will be known as a landscape. That area is known as landscape. So you say it is a landscape of South India or peninsular India, landscape of East Asia, landscape of Africa, in this way. Then we have discussed this non-uniformity that is caused by the arrangement of different landforms in a region. This non-uniformity is known as topography. So these were the basic definition that we have learned. Now, suppose this is a landform. Now, what this landform is made up of? It is made up of some rock. This will be known as a geological structure of the landform. Geological structure, geological makeup of the landform means type of rock. Type of rock, we have three basic types. That is, it can be the igneous rock, or metamorphic or sedimentary rocks. So what is this landform made up of that constitute a geological structure or a parent rock? This is also known as regolith. The basement rock, the fundamental rock of any landform is known as regolith. Now, for example, if this is a Deccan Plateau, what is the regolith of the Deccan Plateau? It is made up of volcanic rock, right? Volcanic in origin. Now, this landform is influenced by two forces. There is something operating from inside the earth. This will be known as endogenetic force, and there is a force operating from outside. This is known as exogenetic forces. So these two forces operate on the landform and they keep on modifying this landform. So what are these two forces now known as? They are known as processes. Right, processes constitute endogenetic process and exogenetic process. Now you tell me which is more continuous process? Which is more continuous? Exogenetic is most continuous, while this may not be continuous in that manner. Now, for example, if it is Himalayas, Himalaya is getting uplifted. There is increase in height of Himalayas by the endogenetic process. But is it increasing continuously on a daily basis or on the yearly basis? No. That this is a slow process or there can be breaks in this event. So endogenesis is not a continuous phenomenon in many parts on the surface of the earth. Rather, atmosphere is present at all the places. Temperature is present at all the places. Winds are present at all the places. Thus, these processes are more continuous in nature. So what is which process has a greater continuity? It is exogenetic. Okay. Now, so this landform is going to get modified. Let us say the landform is now cut into, there is a river which is flowing like this. What this river does is cuts this landform into two. A new landform is appearing like this. So this is a new landform and there is a new structure that has been created by the river. So what is river? Exo, which has modified the landform, creating one valley here, creating a valley, right? Now, how this landform got modified, this also depends on how long this process have operated. So the third factor is what? Time, the duration of that process. Therefore, we are having a basic principle of geomorphology which says landform is a function of three things, that is structure, process and time, right? These are all fundamental concepts, same in optional also, but you should know in GS. Landform is a function of structure, process and time. What is meaning of structure here? Yes, what is a structure? Geological structure. Process means the endogenetic and exogenetic process, but we more focus on which process? Exo, okay, because of its continuity, and time is the duration of the process, duration for which the process is operating. Now, these three factors are responsible for making or creating a difference between the two landforms. Let us say there is a mountain in, assume India, right? And there is a mountain in Kenya. This is Central Africa, right? Both the mountains are made up of rock X and rock X, similar rocks, right? But what is happening here? There is a difference of process. So this is in India, means here there will be rainfall for rainfall is a dominant process and rainfall will occur, let us say, for 4 months. This is in equatorial region. Here also rainfall is there, but rainfall will operate for 12 months throughout the year. So process also is same, but the duration of the process is different. What will be the resultant landform now? Will they be same? No, the resultant landform will be different. It means that if you change any one of these, the resultant landform will also get modified. Okay? So the base rock is known as regolith or geological structure. Process is endo and exo. Time is the duration of the process. Okay? Now, these are fundamental things. You don't expect very like factual part here. You can expect statement and assertion reasons in this topic. Now, so landforms are influenced by two forces. Endo, origin of endogenetic force is interior of the earth. Endogenetic force can create, yes, what they can do? Irregularity on the surface. It will create some unevenness on the surface. It may cause some upliftment, folding, warping in this way. So there can be some irregularity creation of some structures by the endogenetic. It can create some structural feature. Now here the structure means feature, not the geological structure. It can create some unevenness on the surface, or you can write unevenness on the surface. Now, what is exo? Exo has the origin external to the earth. Most of the exogenetic forces, they originate where? The origin of majority of the exogenetic forces is in atmosphere. Okay, it is in atmosphere. What is the tendency of this exogenetic force? Tendency is, suppose this is a landform and exogenetic force is operating on this landform. Over a period, this will be reduced, and finally this landform is going to be brought down to which level? Base level or sea level. So what is the tendency of the exogenetic force? It is to cause degradation of the landform, reduce the existing landform. Therefore, the exogenetic forces are also known as leveling force, destructive, degradational leveling forces. Exogenetic forces are known as destructive or leveling force. Fine. Now we got the identity of the two forces, endo and exo. Now, if I say that a rate of endogenetic force is equal to rate of exogenetic forces, means these two forces are operating with the equal intensities. What will happen to the surface of the earth? Yes, if two forces are operating with the same intensity, what is the surface of the earth appearing now? It will appear flat, it will appear uniform, because when I say it is two forces with equal intensity, whatever is created is destroyed at the same rate. The surface of the earth appears to be uniform. But is it really uniform? No, it means that what is the relationship between these two? It is imbalance. So we can say, what is non-uniformity on the surface of the earth? Landform. So we can say non-uniformity of the surface of the earth is the outcome of imbalance between the endogenetic and exogenetic forces. What is non-uniformity? Unevenness. So can I write landform is the function of endogenetic and exogenetic forces. It is the competition between the endogenetic and exogenetic force. You can mention there, landform is a function of landform is a function of endogenetic and exogenetic forces. Now, if you compare the rate of or intensity of operation of these force, which is operating with the greater intensity, which is more fast, endo or exo, which is more fast, exo. Now, for example, this is the surface of the earth and here is a volcanic eruption, right? Magma is coming out and this magma is creating one mountain of some 1500 meters height. A relief is created. Now, to create this landform, this volcanism has taken a duration of, assume, 3 years. This has been created by 3 years of volcanic eruption. Okay? Now, exogenetic is operating. When I will say that endo and exo is operating with the equal intensity, if same 3 years is taken by exogenetic forces to reduce the height of the landform to base level. But is it that it can be brought down in 3 years? No, it will take nearly 1000 years for the exogenetic forces to bring down this. So, which is operating with the slower pace? Exo is operating with the slower pace. Always the endogenetic compared to exo, the rate of endogenetic forces will be higher, right? Rate of endo will be greater than the exo. Now look at the practical sense of this. Meaning is the time that is required to create any structure by endo is shorter than the time required by exo to destroy that structure. So this is the meaning of intensities. Fine. Now you can take example of this also, like this is the Aravallis. The maximum height of Aravallis was 11,000 meters when it was formed. What is the age of Aravalli? It is 2.5 billion year. It was formed 2.5 billion year. When the Aravallis were created, their height was 11,000 meter, means they were created with the height more than the present height of Himalayas. Okay. Now, last 2 billion year, these Aravallis have been continuously operated upon by the exo, and today we have this. This is the Mount Abu of Aravalli, which has the maximum elevation. How much? It is around 1700 meters. Guru Shikhar, which is 1722, is the highest peak of the Aravallis. Means it. What is the duration for bringing down this landform? It took nearly 2 billion years for degrading the Aravallis from 11,000 meter to 1700 meter. So this is the example where we can understand the process, the exogenetic processes are slow operating processes. Okay, the landform degradation is a slow process. Okay. Now, let us see the endogenetic first. Endogenetic forces. Now, from here it is important for objective questions. Previous for statements. So, two principles we have learned in geomorphology. What is that? Landform is a function of structure, process, and time. So in optional, it is known as a trio. This was given by a geomorphologer, William Morris Davis. That is, names are not important in GS, but remember, this is a principle. Second principle is landform is a function of two processes, endogenetic and exogenetic, or it is outcome of competition between the two processes, endogenetic and exogenetic process. Okay. Now, Let us see endogenetic first. Endo, these are the forces that have origin in interior of the earth. Means to understand the endogenetic force, we have to link it with understanding of interior of the earth. Now, so let us see what is earth. Age of the earth, basic information. Age of the earth is around 4.6 billion years. Formation of the earth. Formation of the earth is from the pre-existing matter of the solar system. This material is known as primordial matter. What is a primordial matter? All that the matter that created sun and all the planets. Okay, this is known as a primordial matter. Now, yes, 4.6 billion, 4,600 million years. Now, you know million, I suppose. Right, 4.6 billion year is the age. Now, this is the geological time scale of Earth. It was formed from the pre-existing matter. Pre-existing matter is, you can say, some matter was rotating in the universe like this, and it got consolidated in this way, and remaining moved out into circles, and in each circle it got again consolidated to create what? Planet. 97% of this matter has remained here, that created sun, and remaining 3% got distributed as planets. And as you move out from the solar system, the density of the planet goes on decreasing. Now, this is the fundamental principle in entire solar system and planet. Moving from center to outside, the density will go on decreasing. That is why you might have studied the inner planets are known as terrestrial, outer planets are known as gaseous. So more density towards the interior, right? So in this way, every planet will differ in composition, every planet will differ in densities. Okay, so there is a density difference. So this matter that created Earth is known as a primordial matter. Initial Earth was having an uneven shape. This was known as a blob. Initial Earth is known as blob, which was uneven, which was not like present spherical Earth. The present Earth, now it got its shape over a period of time. It became spherical and compressed on the pole, expanded on the equator, and this will be known as what? Geoid. So it got a geoid shape. So conversion from blob to geoid. What is a blob? Blob was the irregular shape of the planet when it was born. Now, the temperature, factual parts but important, not there in notes, so write it properly. Primordial and blob. Now, when this Earth was getting converted from blob to geoid, or you look at the temperature of the Earth after formation. Temperature of the Earth after formation was 6,000 degrees. So the surface temperature of the Earth was 6,000 degrees. This was the temperature of the blob, you can say. 6,000 degrees. Now there are two processes that are operating. Two processes. One is Earth started after getting separated from the sun. Earth started cooling. So there was a cooling of Earth. And the second, there was adjustment of densities. So that is known as density adjustments. Density adjustment. density adjustment. What is that density adjustment? That in this blob, all the material that was there with higher density started settling towards what? Center of the earth, and low density material was left near the surface. Okay, so this is known as density adjustment. Now, what is high density material of the earth? That is metallic material, metallic element. What is that? Nickel, iron. These are considered as high density elements. So where they went? They went at the center. That is why the core of the earth will have what? The core is composed of knife, that is known as nickel and iron. Okay, so this led to the establishment of the core. So density adjustment was the major phenomenon which is operating even today, that is resulting in changes in the earth. Okay, so two process, cooling and density adjustment. Fine. Now this is clear. So this is the birth of the planet. Now the cooling of earth. So the outer layer of the earth started cooling first, right? So this was cooling and there was solidification of the matter going on the surface. Okay, the first layer to cool. How was this blob? Blob was semi-solid. It was having lot of gases and semi-solid material, and it started cooling. The outer layer of the earth was first to cool and solidify, and there was formation of rocks, but was it cooling uniformly at all the places? No, this cooling was not uniform. It has cooled here, then cooled in this way, So there were initially some small patches of landmass created, small continent-like structure, small fragments of continent created. What are these initial continents known as? These are known as proto-continents. These were the miniatures of the present day continent. Okay. Solidification, which was uneven, which was differential, created a proto-continent. Then it might have happened that the proto-continents came together, again went back. So this process continues. So proto-continents were the initial continent. Now, so when the rock was created, when the material of the earth have undergone solidification, all the gases that are trapped in this material escaped. ये आज भी होगा. If lava comes out and it is lying on the surface, this lava will solidify, and in the process it will give out gases. Okay, so that has happened in much larger quantity, larger proportion in the past, and this process is known as degassing. This is known as degassing. What is degassing? Escape of gases from the rocks, from the solidification of the rocks. Escape of gases from the solidification of the rocks is known as degassing. Now, what were these gases which were given out by formation of the outer layer? What is outer layer? Yes, what is the outer layer of the earth? Crust. Crust was created, lithosphere was created, and the gases given out by this process, these were carbon dioxide, oxygen, hydrogen, nitrous oxide, carbon monoxide, sulfur dioxide. In this way, these were the gases, right? Now these gases, they started accumulating around the earth, and this was the birth of which sphere? Atmosphere. So what came first, lithosphere or atmosphere? First is lithosphere and then came atmosphere. So this degassing contributed in the formation of atmosphere, and atmosphere was having carbon dioxide, oxygen, hydrogen, nitrous oxide, these. Now, is it that the proportion of these gases that were present some 4 billion years or 3.5 billion years before present, same as the proportion of gases that are present today? No, that composition was completely different. Therefore, that atmosphere which was created at the beginning is known as primary atmosphere, which got modified, which got altered, which evolved into present atmosphere. So today's atmosphere is secondary atmosphere. So it was a change from primary to secondary. Okay. So initial atmosphere was known as primary. The main process that contributed in establishment of the primary atmosphere is degassing. Okay. This was the degassing phenomenon. Fine. So lithosphere, degassing, atmosphere. Now you have here oxygen, then it was hydrogen. This was the surface of the earth. The oxygen was given out, hydrogen was given out. All this combined to form a cloud. Okay, cloud. The temperature of the earth, let us say, was 500 degrees this time. Now this cloud started raining. This raindrop came up to here, got evaporated back because temperature was still high. So I'm talking about somewhere 3.5 billion years before present. Now again, after some time, this temperature became 200. This raindrop came bit closer, again got evaporated. Like this, the precipitation was attempted on the surface. The rainfall was attempted, but this could not be successful for nearly 500 million years. And after some time, that is when the temperature got reduced less than 100, it became possible for rainfall to crash on the surface, and this was 40,000 years of cycle of precipitation, continuous rainfall that has occurred, which emptied all the moisture that was collected in last 1 billion years, and all this water went into the depressions and got accumulated on the surface of the earth, and this was the rise, and this was the birth of oceans or hydrosphere. So इसमें sequence क्या है formation का? Lithosphere, atmosphere, hydrosphere. This was going on for first 2.5 billion years. These processes took nearly 2.5 billion years to set up the system for the life to come into existence. So first 2.5 billion years, there was no life. Okay, there was no life. This period is known as what? It is known as Azoic period. Azoic means without life. And after that, maybe 1 billion year another it took for the small organisms to come into existence. And the present life or well-established life, you see, only last 1 billion year. Now this period after 2.5 to 4 point present, this will be known as, we divide the earth into geological history into two periods, Zoic period and Azoic. Azoic period is the period where life did not exist. Okay, and what was that? The first 2.5 billion years are considered as Azoic period. So all the rocks that were created during this Azoic period, will they have fossils? Will they have fossil? What is fossil? Remains of the life. They will not be having any fossil. These rocks created during this first 2.5 billion year initial rocks of the crust, they do not have any fossil, they are non-fossiliferous rocks. So this period of 2.5 billion year is also known as a Precambrian period. Precambrian, note down. First 2.5, note there, first 2.5 billion years are is referred as, first 2.5 billion year is referred as Precambrian phase. Precambrian phase, characterized by absence of life. Characterized by absence of life. This period was for the establishment of lithosphere, atmosphere and hydrosphere. It is also known as azoic, AZOIC, azoic phase, due to absence of life. Azoic phase due to absence of life. All the rocks created during the Precambrian phase, are, what you will write, fossiliferous, non-fossiliferous, non-fossiliferous, or non-fossiliferous, right? Now, so this is how the Earth's surface evolved. Now we are not concerned much about what has happened to atmosphere. That will be a part of climatology and oceanography. Now look at the cooling of Earth. Now, Earth is formed from the same material of the sun, yes or no? Earth is formed from the same material of the sun. Sun has radioactivity. Thus, Earth also has retained some of the radioactivity in its interior. So there is a radioactive process which is going on, radioactive decay which is going on, which generates the heat from interior of the Earth. Okay? Or in general also, we'll say Earth is, after getting separated from the sun, Earth is losing the heat. And how is the heat transfer? Heat transfer will be from surface to center. Okay, surface to center. The center of the Earth is still retaining the temperature of 6,000 degrees. So we can say these temperatures got reduced to 100, then there is 1,000, 2,000, 3,000, and then 6,000, right? So direction of cooling of the Earth is from surface to center. Principle of thermodynamics. If any body is cooling in one direction, the heat transfer will be in opposite direction. So what will be the heat transfer? Heat transfer will be from center to surface, and this heat is expressed as energy on the surface of the Earth, which is the reason for endogenetic forces. So what is this heat known as? The heat that comes from the interior of the Earth is known as geothermal. Geo is Earth, thermal means temperature, very high temperature that is present inside the Earth. So this is the reason for heat. So it is known as geothermal heat. What is the direction of transfer? Center to surface. Okay. And this heat is expressed in different forms on the surface of the Earth, and this becomes the reason for endogenetic forces. How it is, that I will explain later on. Note down. The transfer of heat is from center to the surface. Transfer of heat is from center to the surface. The source of heat is the radioactive decay. In Earth's interior. Radioactive decay in Earth's interior. Next point. This heat is expressed as energy on the surface. Known as endogenetic forces. So, known as endogenetic forces, right? So, what is the endogenetic force? It is the manifestation of heat, and the source of heat is center of the earth, which gets transferred towards the surface. Now, we have to understand here how can be a transfer of heat. There are three mechanisms generally for heat transfer. One is radiation, then conduction, and next will be convection. In general, there are three mechanisms for heat transfer. So we have to see what is effective for Earth. Now, is radiation an effective mechanism for heat transfer from interior of the Earth to the surface? So, see, this light is radiating, right? So, when is radiation effective? When the medium is transparent. Is Earth transparent? Can we see what is going on inside the Earth? No. So, Earth is opaque or Earth is not transparent. So, radiation is not the effective mechanism of heat transfer from interior to the surface. Here, don't confuse with solar radiation or reflected radiation. That are different things. Solar radiation, some students may be thinking about radiation from the surface. That are reflected radiations, what we receive from sun. Okay, that is another issue. But Earth is not directly radiating out anything as the heat. Okay? So radiation is not an effective mechanism as Earth is not transparent. Number two, conduction. Can conduction be effective for interior of the Earth? What is conduction? Suppose this is a metal bar and I keep on a fire or a candle. Within few minutes, I can feel the heat or temperatures. It get heated. And if I move out of that candle, within few minutes, it will cool. Conduction is a rapid transfer of heat. It will be increasing the temperature rapidly and also cooling rapidly. Heating and cooling, both the process are fast or rapid. If Earth was having a conduction as an effective mechanism, Earth might not have been able to maintain such a high temperature after 4.5 billion years. Earth might have completely radiated everything out if conduction was to be effective, right? So conduction is not effective, but that cannot be a justification that it might have, because there is a rate of radioactive decay also responsible. So on what basis we are saying that the conduction is not the effective mechanism? For conduction to be effective, how should be the composition of that matter? Metallic. Is Earth a metal ball? No. What is the composition of Earth? It consists of silica, then it consists of magnesium, then aluminium, iron, and then it consists of lot of gases like oxygen and that. So major proportion of Earth's composition is what? Silica and oxygen. What are these? These are, now silica. What is this? Is it a good conductor of heat? No, it is a poor conductor. It is not a bad conductor. It is not a good conductor. It is a poor conductor of heat. Majority of the Earth's material is made up of poor conductor of heat, which will not allow this mechanism, this method of heat transfer to be intense. Thus, conduction is there. We are not denying, but conduction is not effective in all the regions of Earth's interior. Conduction is a slow process in many areas of Earth's interior because of the presence of poor conductor. The material of the Earth is poor conductor of the heat. So you can write one statement: majority of the Earth's composition, majority of the Earth's composition is the poor conductor, is the poor conductor of heat, is the poor conductor of heat, which prevents conduction as a mechanism of heat transfer. Thus, conduction is a slow process. Conduction is a slow process. Overall, we are talking about, but there will be some areas where conduction will be fast, but overall rate of conduction is slow. Okay? Now, then comes convection. Now, as a statement, objective question, this is the most effective mechanism of energy transfer. Convection is most effective. Okay? If you are asked in objective type question. Now, so what is convection? Convection is the heat transfer by movement of matter. So convection generally will be in gases, convection will be in liquids. Wherever the material can move, the heat transfer which occurs by movement of material will be known as convection. Jaise, suppose you are boiling water, right? Now the temperature of the water is reaching boiling point. Will it reach directly all of a sudden? No. So what will happen? The first utensil will get heated, then the molecules of water which are attached to the bottom will acquire the heat, they will move towards the surface, then it will be replaced by the colder molecules. In this way, the energy gets transferred. This process is known as convection. या फिर you see, in case of rainfall also, if there is lot of moisture present on the surface and there is very high intensity solar radiation, the surface of the earth get heated, this water vapor will acquire the heat, the air becomes lighter, moves up and forms a cloud, and then there will be rainfall. This rainfall is known as convective rainfall. Okay, such convective rainfalls occur in which region? Equatorial region. Hot areas will have a convective rainfall, or in case of India, coastal areas will have the convective rainfall, right? So convection, it involves movement of matter, Now, so how is this convection in interior of the earth? Now see, this is, now one thing here, what is radius of the earth is 6,400 kilometers. Approx means round figure I am saying. वो NCERT लेकर मत आइए कि 6,300 कुछ लिखा है. So 6,400 kilometer is the radius. So if you see the density of the Earth's interior, let us say it is D1, D2, D3, like this, D4, D5. As we move towards the interior, the density goes on increasing. Like surface has a density of 2.2, the innermost part has a density greater than 13, 13.1, 13.2. This is the density of the core. So density increases with depth. Now, if I take temperature simultaneously, T1, T2, 3, 4, and 5, what is happening to the temperature? The temperature also increases. So both temperature and density increases with depth. Okay? Temperature and density increases with depth. So we use a word differentiation. Differentiation. This is known as thermal differentiation. Density differentiation means every depth of Earth's interior has a different density and different temperature. Clear? So thermal differentiation, density differentiation. Now look at the composition of the Earth. Is Earth homogeneous? Is Earth made up of one material throughout? No. So what is there? Earth is heterogeneous. Agreeing? Earth is heterogeneous. It doesn't have the same material at all the places. Now, suppose there is a material here at this depth, and here the temperature is T4. Now the material composition of Earth is different, means the matter which is present inside the Earth in different region is with different melting points. Melting point is not same. Now here the temperature assume is 4000 degrees. 4000 degrees, and this matter has a melting point of 2000 degrees. What will happen? This material has a melting point of 2000. It is existing in the region with temperature of 4000. This will respond to this temperature and will get converted into what? Liquid. Will get converted into liquid. Now when it is getting converted into liquid, what will be the density of liquid? High or low? Density of the liquid will be low. Let us say the density of this material drops to 2. Now if it is 2 and it is placed inside the Earth, where is the appropriate location of this material? It will be on the surface. Such low density material will try to move towards the surface, and this may be replaced by some high density material. Now this is going on. This is how the material is overhauled. Low density material will be always pushed towards the surface, and in this process of moving toward the surface, what it does? It is going to transfer the heat, and this material, when it strikes the crust, what it is going to do here? It will fold the crust, it will uplift the crust, or it may erupt at some certain places. This will be expressed as endogenetic force. So this movement is known as, what is this process? We have already discussed this. This is known as density. Yes, this is known as density adjustment. So what is density adjustment? Low density material moving towards the surface and high density towards the interior. Processes might be different, that we will see ahead. This is now restricted, right? If you see the present structure of the density adjustment is not at all the places, because this kind of material or that flexibility is not there. But when it was a blob, this density adjustment was very easy, because all this material was flexible. It was semi-solid, it was elastic or plastic material. It was easy to move, but now it is difficult. So that is why the thermal convections may not be present at all the places, though it is the source of heat transfer or energy transfer or endogenetic, but may not be dominant at all the regions in interior of the earth, right? But overall, if you see, thermal convections are the dominant mechanism for heat transfer. Yes, got this. So note there, thermal convective currents develop in Earth's interior. Thermal convective currents develop in Earth's interior as the outcome of density adjustment. That is, low density material moving towards the surface and high density material pushed towards the interior. Right? Next point, thermal convection contributes to majority of the endogenetic forces expressed on the surface. Fine. So what we have learned here, what is the origin of endogenetic? Endogenetic force originate as a mechanism of heat transfer. Now, what is most effective? Convection. Conduction is less effective. You have to tell the reason for that. Okay? Now, these are endogenetic force. Now, to know endogenetic force, we have to study about interior of the earth. Next topic is Earth's interior. So I'm linking from endogenetic force to interior of the earth. Then again back we will move to the explanation for exogenetic forces, classification and exogenetic. Now, interior of the earth, initial part is important for objective question. Okay, so today's class, whatever we'll discuss, that is important for only prelims. Next class will be important for mains. Now, why it is important to know the interior of the earth? Because see, when we started the subject, we said that the focus of geography is on the surface of the earth. Okay, being a geographer, why we should also be aware about what is happening inside the earth? The reason is whatever operating on the surface, whatever configuration of the surface of the earth is, it is the outcome of interior. Okay, so note there. The distribution of geophysical phenomenon Geophysical phenomenon means which originates interior, like volcanism, earthquake, all these are known as geophysical phenomenon. Distribution of the geophysical phenomenon and configuration of surface. Configuration of the surface means arrangement of the landform is the outcome of phenomenons operating in Earth's interior. Now, so it is important for a geographer also, for a geomorphologer also, to know about, to certain extent, interior of the Earth. Now then the question is how to study the interior, how we can know about the interior of the Earth, because radius is 6,400 kilometer, temperatures are very high, temperature goes on increasing. In such environment, is it possible to collect the data directly from the interior of the Earth? So here we have developed two methods to study the interior. First is through direct evidence, direct evidences, and second is indirect evidences, direct and indirect evidence. What is meaning of direct evidence? That is accessing the physical environment directly inside the Earth, or measuring the temperatures directly from interior of the Earth, or getting the material from interior of the Earth and analyzing it. These are known as direct evidence. So what will be, how we can get the direct evidence? We can get the direct evidence from mining. We can also get the direct data from drilling of oil wells and all. And can I write here the direct evidence is also volcanism? Volcanism is a direct evidence, correct? But if you say you are collecting the data of temperature from mining or drilling, or you analyze the rock coming out from the volcanoes or in the form of lava, what is the depth of volcano? Is it that the volcano comes from the center of the Earth? No. Most of the volcanoes, they are erupting from first 100 to 150 kilometers. Majority of them erupt in this depth. Mining, the maximum depth is like 7-8 kilometer. Drilling, if you say, it is maximum 15 kilometers we have drilled. So is it that the direct evidence sufficient for interpreting entire interior of the Earth? No, this is not sufficient, right? Thus it has to be supported by some indirect evidence. It has to be complemented by indirect evidences. So what are indirect evidences? Those interpretations without physical access to the interior of the Earth are known as indirect evidences. What are these? This you can get from the behavior of earthquake waves, data collected from the seismic wave, data of the seismic wave. Yes, this part is clear. So there are limitations to the direct evidences. Okay? You have to, because of limitation, we have to complement the data of direct with indirect. Means direct evidences alone cannot help us in approximating what lies inside the Earth. It has to be supported by indirect evidence. Okay? So indirect evidences from seismic waves. Second, indirect evidences also can be from geomagnetism, magnetic property, magnetic field of the Earth. We have a topic ahead, geomagnetism, and yeah, so these are direct and indirect. Now if I say this is Earth and there is some meteorite here. Now, can this meteorite also provide us information about composition of interior? Huh? Can meteorite provide? Why? Because yes, good. This is made up of same primordial matter. So what is this meteorite? Should you place it in direct or indirect? Huh? Direct or indirect? This is indirect evidence because this doesn't belong to the physical environment of Earth's interior. So it is indirect evidence. Meteoritic evidences, this is indirect. Anything you collect directly from the interior of the Earth, that will be a direct evidence. Okay? Now, so there are certain projects which are taken up by different countries to collect this data for approximation of the Earth's interior. So, like first one, just note this. These are some drilling projects. We are drilling into the interior of the Earth and collecting the data of temperatures, data about the rocks, material. More we are collecting the temperature data, and based on the temperature data, we are approximating about what can be ahead, what after certain depth, what can happen. But still, see, all these things are approximation. It is said that we are only 10% aware about geosphere, 90% aware about atmosphere, right? Like us also, we are more aware about outside, what is going on with others, right? And we are less aware about what is there with ourselves, right? Interior अंतरात्मा का तो पता है नहीं, ठीक है? So projects there, these are, number one is Kola Super Deep Borehole Project. Kola Super Deep Borehole Project. This is taken up by the agency of Russia. This is in the region of Kola Peninsula of northwest Russia. Number two is Pacific Super Deep Project. This is on the floor of Pacific Ocean, drilling on the floor of Pacific Ocean. This is by Japan and it is close to Japan Islands. Pacific Super Deep Project near Japan, taken up by Japan. See, Kola Peninsula, it is the deepest terrestrial or land-based drilling project. Pacific is the deepest ocean-based drilling project. Okay, this here we have gone up to 15 kilometers. Here it is something like 12 kilometers. Now, third is Mohole Super Deep Project, MOHOLE, Mohole Super Deep Project. This is in the region of Florida. This is United States of America. This is land-based drilling. Florida, United States. Then there was also some data obtained from some oil drilling. We have used some data about the interior of the Earth. One of the prominent oil wells where we used the data was Al Shaheen. Al Shaheen oil well drilling. This is of Qatar, Gulf country. Al Shaheen oil drilling. This also contributed to the temperature data. Then it was the data obtained from the Kimberley mining. These are Kimberley mining is of South Africa. This is the diamond mining. Kimberley mine. First three are more important. See, Kola Peninsula region is in news, so focus on the first one. In India, we have a similar project initiated by the Ministry of Earth Science. That is, this is at very nascent stage, but important. Koina Super Deep. project. This is in the region of Koyna Dam, that is of its state, Maharashtra. Koyna Super Deep Project. This is the land-based drilling in Koyna region of Maharashtra. This is the nodal agency will be Ministry of Earth Science. So last one and first two, remember that. Now, this is the region of Kola Peninsula on the map. Here it is White Sea and you have a Barents Sea. This one is the Kola Peninsula, which is sharing the border with, what is the country here? Norway. So this region is known as a Kola Peninsula, which is bordered by two water bodies. Here is the North Sea. This is Norway, Sweden, is Northern Europe, bordered by White Sea and Barents Sea, B-E-A-R-E-N-T or R-A-N-T. So you can find on atlas later on. Kola Peninsula is the province of Russia. This belongs to Russia and shares the border with Norway. Instead, you have to look at atlas later on. Okay, you just draw rough. Fine. So these are some projects which are operational, which are where still drilling is going on. Kola is still active, even Pacific drilling is active. So we are trying to go deeper and deeper, collect more and more data on temperature and simulate this data for mathematical modeling of temperature behavior in interior of the Earth, right? So now, so study of interior of the Earth that began at the start of 20th century, around 1900. We were having certain models given about the interior of the Earth. And as our investigation and tools, methods have changed, we came to know more and more about what is lying inside the Earth. In this way, our way of understanding and the model of interior of the Earth over a period have changed. But we can classify the Earth's interior based on three models. There are three models which were given over a period of time. So the first model, which was given around 1900, was based on composition. This was the first model of Earth's interior in 1900. This was in use up to 1940s, up to Second World War. All the theories that were given were based on this model. First model, which divided Earth into three layers with three different material. The outer layer, see composition, difference in material. The outer layer is known as Sial. The intermediate layer was Sima, and the center of the Earth was knife. So concept of Sial, Sima, knife was given, but this model contested that the thickness of Sial, Sima and knife is almost uniform. that later on was rejected. Okay, but composition wise it is true. The outer layer of the earth is still consisting of sial, the innermost part is knife. So there are three layers of earth's interior based on the first one. Number two, the second model was based on density. This was in use from 1940s to 1960s. It is in use today also. This was based on density. So according to this, the interior of the earth consists of three layers. The outermost thin layer is known as crust. The intermediate layer is mantle, and the center of the earth is known as core. So crust, mantle, core. These divisions are based on density. So here density of the crust is less than density of mantle is less than density of the core. Core is at the highest density. Now if you combine the previous with this, you will get the answer. Why is density of the core highest? Because of concentration of metallic elements. Okay, that is knife. So lighter material, crust is made up of Cr, and you can combine this. Okay, so what is mantle composed of? Sima. Now it became in this way. Cr, the outer layer of the earth is crust or Cr, intermediate mantle or Sima, the center of the earth is knife. Now, so if you take a cross section of the earth's interior like this, this is from the sea level, this is the center of the earth. What is this? 6,400 kilometers. This is the radius. So the outermost layer is crust. What is the thickness? Average thickness of the crust is 40 kilometers. Crust is extending up to 40 kilometers. Okay? And from 40 to 2,900 kilometers, this is going to be mantle, and from 2,900 to the center of the earth is core. Now there is a division, means what? There can be a theoretical boundary to show the difference between crust and mantle. So this is known as discontinuity, a boundary between the crust and mantle. This is known as Moho or Mohovric, after the name of geologist. Moho discontinuity. What is Moho discontinuity or Moho boundary? It is between crust and mantle. And between mantle and core, boundaries are important for objective question. Between mantle and core, there is a boundary. This is known as Gutenberg discontinuity. Gutenberg, between mantle and core. So Moho discontinuity is crust and mantle core is Gutenberg, right? So this was the second model around 40s, 50s and 60s. This was prevalent. Even today also we use the term crust, mantle, core as basic thing about the interior of the earth. The third model, which is more recent, or this is used in the modern theories, is based on the state of matter. Based on the state of matter. State of matter means whether the matter is existing in solid, liquid, semi-solid states. Based on the state of matter, here earth is divided into the outermost layer of the earth is known as Now this is known as lithosphere. Lithosphere, which is made up of rocks. Lithos means rock, and the depth of lithosphere is 100 kilometers. 100 kilometers. Some books you may find 150, fine, but 100 is standard. So 100 kilometers is the depth. And what is this? What is the state of this? Solid. Lithosphere is solid. Then we have the remaining part is mantle, but below this lithosphere up to some 700 kilometers, this one, from 100 to 700, 100 to 700 kilometer, this layer is known as asthenosphere. Asthenosphere is semi-solid. Now, do not worry about the reason for this. We'll have a discussion on that. As first, take the factual part. Asthenosphere, it is between 100 to 700 is the thickness. It is semi-solid, and then remaining from 700 to core. What is that boundary? 2900. This is a part of mantle. So from 700 to 2900 kilometer, this is going to be mantle is solid. Mantle is solid, and then core. Core is divided into two parts. 2900 to 5200. 5200. This is the outer core. Outer core is 2900. Which boundary it is? 2900 is which boundary? Gutenberg discontinuity. So 2500 to 5200. Some books 5300. Okay. This is outer core. And how is outer core? Is liquid. Outer core is liquid, and remaining part, that is 5200 to center, that is 6400, is inner core. This is solid. Inner core is solid. Okay. So what has happened here? We have divided core into two parts, outer core and inner core. Outer core is, yes, outer core is liquid, inner core is solid. Mantle we have divided into two. Upper part of mantle consists of asthenosphere, and then it is lower mantle. This is upper mantle, lower mantle. How is upper mantle? Semi-solid. Lower mantle is solid. Okay? And the outermost layer is solid, that is lithosphere or crust. Now, this is just a rough expression. You will be getting more idea. This you have done. Look at this diagram. This will be more important and easy also. Now, this is the surface like this. We'll make a cross section again. Now, here is, this is 2900. First mark what we know, 2900. This is 6400 kilometers. What is this? This one is core. This boundary is Gutenberg discontinuity. Fine. Now, what we got, the outermost layer of the earth, which consists of continents, oceans, and that is existing up to 40 kilometer. What is this? This one is crust. This is crust. Crust is up to 40. What is this boundary? Ye batao. This is moho. Good. This is a Moho discontinuity. This is at 40 kilometer. Fine. Now from 40 to 2900, what is this entire? This is mantle. This is clear to everyone. इसमें कोई दिक्कत? Now, here further division. We'll look at the easy part first. Core is divided now. Core is divided 2900 to 5200. This is going to be outer core. Outer core. How is outer core? Outer core is liquid. This is liquid. Then 5200 to 6400. This one is inner core, and this is going to be solid. Fine. And the entire core has a domination of what? Knife. This is made up of knife. So I'm combining all the previous. Now, there is difference of density between outer core and inner core. Yes or no? Yes. So this also can be one boundary to differentiate the material. And this is known as a Lehman discontinuity. Lehman. Lehman discontinuity, that is between outer core and inner core. So we got three names here: Moho, Gutenberg, Lehman. Now this is clear. Reasons, don't worry. Now move to this region. Now from mantle, first 100 kilometer, this is going to be a solid what? Lithosphere. Okay, lithosphere here up to 100 kilometers. Now from 40 kilometer to, we'll take first 700 kilometers. 700. What is this? This will be upper mantle. 40 से 2900 mantle है, ठीक? 40 to 700 is upper mantle. In this, at 100 there is a boundary of lithosphere. What is remaining then? 100 to 700 is, what is this? Asthenosphere. Asthenosphere. And this asthenosphere is in semi-solid state. Asthenosphere is in semi-solid. Now here, be careful for this part. Yes, all of you are following this. Now, what is lithosphere? First thing here, it will be in this way. Crust is a part of lithosphere, or lithosphere is a part of crust? Crust is a part of lithosphere. First 40 kilometer of lithosphere constitute crust, and from between the lithosphere starts asthenosphere, and starts mantle, and upper mantle consists of asthenosphere and a part of lithosphere. Will it be okay to say that entire asthenosphere is a part of upper mantle? Yes or no? Entire asthenosphere lies in upper mantle, correct? Yes. Entire lithosphere lies in upper mantle? No, this will be wrong, because half part of lithosphere is the part of crust. Okay. Lithosphere is not entirely present in the upper mantle. Only lower part of lithosphere constitutes the upper mantle. From 700, what is this? This is 700. So 700 to 2900, what is this? This is going to be lower mantle. So how is lower mantle? Solid. And it is made up of, yes, all this region constitutes sema, and lithosphere is solid, and made up of what? Cr, or crust is made up of Cr. Crust is made up of Cr. Below crust, you have a transition into different material. So, can we differentiate between the crust and lithosphere? Can we differentiate between the crust and lithosphere? We can differentiate in terms of what? Composition of rocks. Okay, so crustal rocks will be more made up of lighter material, that is Cr, and rocks of remaining part of the lithosphere below the crust, this will be more made up of magnesium, or it has a dominance of magnesium. So there is a difference in the rock of crust and rock of the lithosphere. So can there be a difference of density between asthenosphere and mantle? Difference of density in asthenosphere and mantle? Yes, there is a drastic difference here, and this boundary is known as a Repetit boundary or Repetit discontinuity between asthenosphere and upper, that is upper mantle and lower mantle. It can be questioned in this way: upper mantle and lower mantle, or it is asthenosphere and lower mantle. The boundary is known as the Repetit discontinuity, right? Repetti, or REPI also in some text it can be. So REPETTI, Repetit boundary. So how many we got? The first one is Moho, then Repetit, Gutenberg, Lehmann, right? Now, can we differentiate here? Already we have discussed, differentiate between the rocks of crust with remaining rocks of lithosphere? Yes. So there is a possibility of a boundary here also, and this boundary inside the lithosphere, which is used for differentiating the crustal rock with remaining part of the lithosphere, is known as, this will be known as Conrad discontinuity. Okay, note down Conrad discontinuity. This is a boundary between the rocks of the crust and remaining part of the lithosphere, rocks of the crust and remaining part of the lithosphere. This is also used to differentiate between the continental crust and oceanic crust. Continental crust and oceanic crust. Now, so this is the uppermost boundary. This will lie within crust. After that, it is Mohoric. Time being, you just understand this Conrad boundary is located within the crust. Okay. Now, this is the difference of rock. We'll see it later when we discuss about the ocean floor. This you time being ignore first. Now, this is clear to everyone. Mohoric, Repetit, Gutenberg, and Lehmann. Now concentrate here. Moho and Conrad are not same. I will tell you the difference later when we move ahead. Now, see, this is, what is the temperature at the center of the earth? Temperature here is 6000 degrees. So heat transfer from inner core. Mechanism of heat transfer क्या होगा? Solid and metal process is conduction. Conduction will be a rapid and intense phenomenon for inner core. All this energy is conducted and transferred to outer core. Outer core is liquid. It can be anything but metallic here, liquid and metallic. So what will happen to the material? It will start moving upward like this. What is the process? Convection. Process is convection. This energy get incident on the mantle, lower mantle. What happens here? It is solid but sema. There will be a process of conduction. Is it intense or slow? This slows down. Here it slows down. See, conduction intense, inner core region is metals and it is solid. Convection in outer core, it is liquid and metallic, intense. Then mantle, lower mantle, conduction, but slow because there is a presence of silica, poor conductor, right? So lower mantle has a slow conduction. Lower mantle has a slow conduction, and all this energy get incident on asthenosphere. Asthenosphere is semi-solid, flexible. So what happens to the material? It starts moving. Then this is again what? Convection. This is known as thermal convections operating in asthenosphere, which get bombarded on lithosphere. Okay, it is going to get incident on lithosphere, and this energy get expressed on the surface as endogenetic forces, right? So how is the energy transfer from the interior of the earth to the surface is a complex phenomenon and a combination of conduction and convection. Whatever endogenetic forces are experienced on the surface, on the lithosphere, is the outcome of thermal convections operating in which layer? This one as the immediate, right? Now, are we experiencing any thermal convection of the core directly? No, this energy is not directly hitting the surface. There is some material in between which prevents the transfer of heat. What is that material? Which is acting as a buffer zone in between. Which is acting as a buffer zone? Mantle. Okay, mantle acts as a buffer zone which prevents the direct transfer of heat to the surface. It slows down the transfer of heat, right? So note down. Yes, this is clear to everyone. Now, note. Which one? I'll tell you. Look into. What? Mixture of? See, where is Cl? Highest concentration of the Cl will be in crust. As we move down, it enters the transition from Cl to sema, means lower part. So if you are taking a lithosphere and you see the crust here, this is the crust and this is a remaining part of lithosphere. This will be dominated by Cl and here will be a start of sema, means you will find a difference of rock. Okay? Now, so note there, the heat transfer mechanism of the Earth's interior is complex. Heat transfer mechanism of Earth's interior is complex and it consists of a combination of conduction and convection. Conduction and convection. The endogenetic forces experienced on the surface are due to thermal convective currents of thermal convective currents of asthenosphere, right? Thermal convective currents of asthenosphere. Now, see this. So this is, let us say, a continent, and here is the ocean floor. From the continent, if you go down into interior, this is going to reach some depth. Let us say this is reaching the depth of 40 kilometers. This is the depth of a continental crust. And if you see here, this is ocean. This oceanic crust is, say it is a 20 kilometer. So there is a difference between the thickness of a continent and thickness of oceanic crust, right? Now, if you see the lithosphere or characteristic of the lithosphere, now this is somewhere the start of mantle. Now here is the boundary where we can differentiate between the crust of a continent with the crust of ocean. Okay, crust of ocean. This is known as, this will be known as a Conrad discontinuity. Okay, so it is a boundary used for differentiating the crust of continent with the crust of the ocean, because the thickness of, see, more elevated, more deep, right? Less elevated, less deep. This is like a principle of our construction of buildings. More height of the building, greater will be the depth or roots also. Okay, this is a principle of isostasy. Yes, getting this? Conrad, we can mention there, it is used to differentiate between the main purpose of Conrad is this. Note, Conrad discontinuity is used to differentiate between the crust of a continent with the oceanic crust. But how much is the depth of the continent? That is not restricted to Mohoric. This you understand. This is not restricted to Mohoric. It can even extend deep into what? Lithosphere. It can extend deep. That is why there is a difference between the Mohoric boundary and Conrad discontinuity. So it means that when you see the rocks of continent, they are made up of, yes, lighter material, more elevated, lighter. Rocks of the ocean floor are made up of denser material. And here is somewhere a boundary between lighter material and denser material. This is known as a Conrad discontinuity. But this is not going to be same at all the places. That is why we are not able to draw it. Okay? Now, see this. This is the surface of the earth, and this is a lithosphere. Lithosphere is extending up to 100 kilometers, and below this up to 700 kilometer is asthenosphere. Now what is going on in asthenosphere? There is a continuous movement of material, like there is a movement of material in the asthenosphere. These are known as thermal convections which are operating. Now thermal convections operate because of heat generated in asthenosphere and also the heat that is coming from interior of the earth, or geothermal heat. Now this is the lithosphere, and you have a thermal convection here. Now, will it allow this thermal convection, allow this lithosphere to remain continuous and uniform? No. What this thermal convection or this energy has done, it has divided these lithosphere into number of segments. This got fractured. The lithosphere got fractured. It has become discontinuous, and we got a segment of a lithosphere now. This will be known as what? Plate. Each segment of the lithosphere is known as a plate, right? Now this is like a principle of buoyancy. So you have a water and you keep a wooden blocks on water, right, of different size. So each of these wooden block of different size, it will sink at different level into the water. Same thing is happening with lithosphere. These are the blocks, and with because of their density, they sink at a differential rate into what? Semi-solid material. What is that? Asthenosphere. Okay, so these are the plates. Now, is this plate going to be stable? No, this plate is, because नीचे कुछ wheel की तरह घूम रहा है, right? There is a convection, there is a conveyor belt which is operating. This is going to cause the movement of the plate. When this plate move, they will interact with each other, and this will be known as tectonics. The interaction of the plate is known as tectonic. So this is going to produce most of the features on the surface of the earth. So what is the main source of energy for tectonics? Thermal convection. Okay, thermal convection is the main source of energy, or that is geothermal heat. Fine. Now, how is this plate moving? This plate. What will be the direction of movement of this plate? Anyway, this we will be discussing in detail, but as it is related to interior, some idea. This plate is going to move in this direction because it is the direction of thermal convection. This plate will move here in this direction. What will be at the junction of the plate? Two plates are colliding with each other. इसको हम बोलते हैं boundary. What is this boundary? Convergent. This is convergent. Here what will happen? This plate is moving in opposite direction. Two plates are moving away from each other. The boundary is what? Divergent boundary. So in this way, based on the direction of thermal convections, we get convergence and divergence of the plate, and plate defines majority of the surface features on the earth. Fine. So this is about the heat transfer, but still we will discuss about the Conrad again. At this point of time, leave about the Conrad boundary. If you are having some doubt or confusion, we'll discuss with the continents ahead. Now, so next is note down behavior of temperature, pressure, and density. All important for objective questions. Behavior of temperature, pressure, and density in interior of the earth. So what we can conclude, all these three variables, how they are behaving, temperature, pressure, and density will, yes, increase with depth. Okay, increase with depth. Density is increasing. We know the density adjustment is the factor. Material composition is the factor. State of matter is a factor for density. Now, what about pressure? Pressure inside the earth. Temperature is increasing. Temperature is reaching maximum of 6,000 degrees. What about pressure? Here, pressure is not inversely proportional to temperature. Pressure is also going to increase. This is not a gaseous open system, what you might have studied in your chemistry. So here, what is the pressure at this point? Let us say P1 is the weight exerted by the overlying material. What is pressure at any given point inside the earth? Is the load that is exerted by the overlying material. Okay? Weight exerted, load exerted. So at this point, it is the load exerted by overlying material. If you go to this depth, this is P2, what will happen? The load exerted is of this much material here. Therefore, the pressure at P2 will be greater than P1. If you go here, this is the weight exerted by what? All the higher material, this is P3. Like this, as we move towards the interior, weight exerted by the overlying material goes on increasing. Thus, pressure also increases continuously up to the center. Which part of the earth's interior is experiencing highest pressure? Huh? core. In that also, inner core is experiencing highest. So this is inner core and it is experiencing pressure from all the direction. So what is the pressure at inner core? Is the compression or compressive force acting on this inner core from all the direction. What is the material composition? Knife. So metal and compressed. It is tightly packed, and in spite of high temperature, this pressure is not allowing the material to change the state. That is why the inner core is in solid state, right? So what is the main factor? Temperature is not a main factor here. So we can say inner core is in solid state because of density, that is knife, and second here is pressure. But the main factor here will be what? Pressure. Now if I say knife is the factor for inner core to be in the solid state, now you take iron and nickel and throw in the furnace of 2000 degrees, okay, what will happen? They will melt, right? Then alone this cannot be a factor for inner core in the solid state. So it is the combination of two, that is metal with compression. Okay? So mention there, the inner core exists in the solid state in spite of very high temperature, in spite of very high temperature. This is because of compression caused by overlying material. Compression caused by the overlying material. In bracket you can mention this prevents the matter, bracket, this prevents the matter, what? Prevents the matter to change the state. This prevents the matter to change the state. Fine. So you got an idea of pressure, why pressure is increasing. Now let us see temperature. Objective question, statement, assertion, reason for this topic. Temperature in interior of the earth increases with depth. ठीक? Source of heat lying inside the earth, that is radioactivity, geothermal, that you know. Now, is increase in temperature inside the earth at the uniform rate? Is it increasing uniformly? Yes. Is temperature increasing uniformly, or rate of increase in temperature maintained same throughout the interior of the earth? No, it is not increasing. So increase in temperature inside the earth is not uniform. It varies. Increase in temperature varies. Now, so what is the direct data about the temperature? Like how is the behavior of temperature in the outer layer, that is crust? So we have 1 degree increase in temperature at 30 meters. 30 meter. Every 30 meter, if you are drilling down into the crust, you will experience 1 degree increase in temperature. This is the rate of increase in temperature in the crust, in lithosphere. Okay? If this is followed, assume, why is that the temperature behavior not uniform? So you have to understand this. If I say that this increase in temperature or this rate of increase in temperature is followed up to the center of the earth, how it appears? Every 100 meter, there should be roughly 3 degrees. Okay? every 1,000 meter means 1 kilometer, there should be 30-degree increase in temperature. Radius of the earth is 6,400 kilometers. So what should be the center of the earth having the temperature? If you multiply 30 with this, it will be more than or approximately up to 2 lakh degrees. Is it possible that the temperature of the earth has, or earth is having a temperature of 2 lakh degrees? No, because we already have the evidences from the primordial matter, the external conditions of the sun and other planet. We have approximated the temperature in the range of 6,000. That can be the maximum temperature that earth has experienced. So when the temperature cannot go beyond 6,000 and it has to reach maximum of 6,000, it is not possible that this rate of increase in temperature is followed up to center. So if you want to reach from 1 degree or 1 degree 30 meters, but you have to reach 6,000 degree at 6,400 kilometer, means what? At some places you have to stop, some places you have to slow down, some places you have to become constant. The temperature have to become constant. Thus we say the rate of increase in temperature in interior of the earth is not uniform. Got this concept? So you can write one statement there. With the normal rate of increase in temperature, with the normal rate of increase in temperature, earth will experience more than 2 lakh degrees. Earth will experience more than 2 lakh degrees at the center. Next point, there are evidences of maximum temperature of earth around 6,000 degrees. 6,000 degrees. Thus increase in temperature in interior of earth is not uniform. Fine. Now we'll see the change, how the temperature is changing. So x-axis will take temperatures and y-axis is depth. Here is lithosphere, then this part is asthenosphere. Already we know the depth here, 100, 700, and here is 2,900. This one is the lower mantle. This is outer core, and this one is inner core. Now, so in lithosphere, the temperature up to 100 is increasing with the normal pace. After reaching 100, there is sudden spike in temperature and it crosses 2,000 degrees just within 150 to 600 kilometers. Okay, within 500 kilometers, there is increase in some 1,500 degrees in asthenosphere. Means there is a spike in temperature, and after this, the increase in temperature is slowing down. It slows down and then reaches to somewhere around 5,500 degrees here, where at the boundary of mantle and core. Okay, and after this 5,500 degrees, a slow increase in temperature is recorded and then in inner core it is reaching the temperature of 6000. So can we say that the temperature in the core almost remains constant? Yes, this is appearing like almost the same temperature throughout the core. Means we can say the temperature is stabilizing. Temperature inside the earth stabilizes at which boundary? What is this boundary? This is Gutenberg discontinuity, mantle core. So temperature in the core remains almost the same, or there is very less difference between the temperature of the outer core and inner core. ठीक? See, now in this case, what is happening? You see the temperature is 500 kilometer distance depth, and increase in temperature is, let us say, 1500 degrees. 500 and 1500 degrees means per kilometer increase in temperature, it is around 3 degrees. Okay? Just to understand the difference. Now from 700 to 5500, 700 kilometer to 5500 kilometer, this is roughly 4000 kilometers. Okay, assume 4000 kilometer. The temperature is increasing from, so it reaches something like 2500 degrees here, 2500 to 5500. So what is the increase in temperature? Some 3000. So per kilometer is less than 1 degrees. So rate of increase in temperature कहाँ पर ज़्यादा हुआ? It is in asthenosphere. Asthenosphere increases. Now numbers are not important. Understand the concept. There is a higher rate of increase in temperature in asthenosphere, and this increase in temperature is melting the material in this region and converting the asthenosphere into semi-solid. This increase in temperature converts the asthenosphere into semi-solid. Now the question is, why it is increasing with this rate? It is because in the process of density adjustment, what has happened? Some of the primordial radioactive substance got stuck up in this area, right? What is asthenosphere having? It is having a concentration of the radioactive elements. One highest concentration of radioactive element, where it is? Core, right? The next region of concentration of radioactive element is in asthenosphere. This is undergoing decay, this is producing the heat, and this is the reason for increase in temperatures. Okay? So you can mention there, asthenosphere has a concentration of, now this is the makeup of the earth itself. Asthenosphere has a concentration of radioactive material. Radioactive material. It is undergoing a decay. It is undergoing decay and contributes to high temperatures. In bracket, reason for semi-solid material, right? Reason for semi-solid material. Fine, this is clear. So radioactive elements, they got stuck up here during the adjustment of the material after the blob, and they today undergo decay and produce the heat, that is temperature. But is it that the asthenosphere is of uniform thickness at all the places? Yes. Is it same thickness at all the places? No, it varies, because this material is not in uniform quantity at all the places. Thickness of asthenosphere differ. If the thickness of asthenosphere is differing, is it that the thermal convections are of same intensity at all the places? No. If thermal convections are of not same intensity, is the plate movement uniform at all the places? No. If plate is not uniform, is interaction of the plate uniform? No. If interaction is not uniform, you will find all these geophysical phenomenon that are endogenetic forces that are experienced on the surface also will not be uniform. In this way, it is linked. Okay? Now, so just here, remember this part, why asthenosphere. Now look at this. Now, can you tell me why is this increase in temperature in the mantle slowing down? Yes, online students. Why is this increase in temperature in, lower mantle slowing down? Yes, good. Here you can look from bottom to top. The process of conduction here is slow because of SEMA, because of poor conductor, right? So this is the reason. Now in this way it reaches maximum here and remains same throughout. I am assuming that it is constant. So how is outer core? Outer core is liquid and inner core is solid. Okay. Assume that temperature here is 6000, temperature here also will assume 6000 for the sake of simplicity. Okay. Now meaning here, if it is liquid, it means that the melting point of this material of outer core should be greater than or less than this. Less than, it is less than 6000 degrees. And if it is 6000 but maintaining the solid state, तो क्या होगा? Melting point is greater than, it needs much more temperature than 6000 degrees. Now here it means that we have to see the difference of melting point, reasons for difference of melting point. Now what contributes to the difference of melting point in outer core and inner core? Can we say the composition is responsible for difference in melting point? Composition responsible hai? Yes? No, because composition in entire is what? Knife. Okay, composition is not the reason. Then what can be the reason? We have already discussed. The reason is what? Pressure. Okay, so pressure operating on the inner core is very high. This increases the melting point. Indirectly, the meaning is this, right? So here you can add one line. The inner core experiences very high pressure. The inner core experience very high pressure, which increases the melting point and prevents it from the changing of state, prevents it from changing the state, or it retains the solid state. Fine. Now this is clear to everyone. Here, why is this mantle experiencing slow increase in temperature? This is because of slow conduction caused by SEMA. Okay? This is clear. Why is this asthenosphere and what is the impact of asthenosphere on the lithosphere? Fine. So this is about the first part of interior of the earth. So we have discussed models of interior, temperature, density and pressure inside the earth, and graphical representation. Now graph and all you need not draw in GS, you can just write these things. If it is optional, graph will be useful. Fine. So we'll stop for the day. Fine. And next class, read this part from NCERT, landform chapter or interior of the earth chapter. But the first part what I have given about models and all you will not find in the book, so better to refer the notes for those things. Mantle is having a slow increase in temperature because of slow conduction. Yes, everyone have followed this? Don't say because you are hungry. चलो हाँ बोल देते हैं, निकलते हैं, टाइम हो गया है सर. This should not be. You got the notification of change of class today? Fine. Yeah. Remaining we'll discuss in next class. Thank you.